All right, so yeah, this talk, if I can get a PowerPoint to move along here, there we go. This talk is really going to focus around HSM challenges that, while not particularly novel, the use cases in the cloud make them stress them out a bit. And so I'll start with a review of HSM architecture for anybody that's not familiar with it in Lustre. I'll cover, how this is generally reused on-prem and how that kind of combines with DR on-prem, how these usage patterns change when you move into the cloud, some architectural challenges that arise, and some areas of improvement, at least as far as I see them. So a quick review, and this is kind of my own definition. HSM is any software architecture or framework that facilitates movement of data between cost and performance differentiated storage tiers. I think there are other differentiations between a variety of tiers, some of which were covered today in other talks that motivate HSM, but cost and performance are really the two main ones. And the HSM frameworks that lead in this regard are generally automatic and transparent to the end user, which is just super important. Otherwise, it becomes difficult to use them. So this is a quick recap of components in Lustre that kind of serve as the main HSM components. There's the MDT, the HSM coordinator, the copy tool, and then optionally a policy engine. So the MDT at the top basically runs on the MDS node. It's in kernel space. It tracks file states going between not even tracked at all through to archived, whether it's been changed in Lustre, not present in Lustre, but present in archive, et cetera. It will translate actions asked of it into actionable commands for the coordinator to carry out, which runs in the case of a single MDS on the same node. And that is also running in kernel space. It'll receive these commands, communicate them to agent nodes running copy tools. And as they kind of complete that work, it'll stay in communication with them, make sure they're still running effectively, et cetera. The copy tool is existing in user space on a client node or an agent node if you look at some of the documentation online, carrying out basically this movement of data in or out of the cold tier. It is really specifically designed to move data to or from a specific end or target cold tier. So if it needs to talk, S3 or Azure Blob or just POSIX, these copy tools are really designed for a specific cold archive. And then last, the policy engine, while optional, basically is the one that admins will set up with a variety of policies to carry out things like, I've reached 80% capacity, I need to free up sufficiently cold things so that I have, the more interesting working set size in Lustre, and I'm not going to run out of space on a specific OST. This is a really simplified diagram of HSM architecture to kind of bring all those things into a visual for people. You can see on the left side, foreground clients initiating some load against the MDT, opening files and whatnot, as well as the policy engine communicating with the MDT to, say, kick off an archive or restore operation against a file. Those communications are being translated and communicated to the coordinator. The coordinator is queuing up those actions and engaging the copy tools to carry them out to a variety of different backing cold tiers. And then they're either sending data out to the cold tier or slurping it into the OSS as shown in the diagram. So a quick note on the external policy engine. I mentioned it was optional. I think that's technically true, but from a tractability perspective, isn't completely honest. Trying to write manual, write your own scripts or do this manually in a very large system becomes intractable fast. And so Robinhood is the most popular incarnation of something like this. It's what I'm going to be referring to for the rest of this talk. It tracks the full namespace of Lustre and SQL tables. It does only track one namespace. So multiple Lustre systems will require multiple Robinhoods, but point being, it can answer really quickly since time t what has changed. It will also, use change logs after an initial scan to track changes, and admins and users can build policies around this. So typical on-prem HSM and DR usage. I wanted to highlight that, like RAID, HSM isn't backup. It's really just solving a problem of how do you accelerate your current workload and your working set size with the hottest tier of storage, presumably Lustre here. disaster recovery is really solving the, if I lose part of my system or my entire system, how do I recover from that situation? On-prem will use one or both, typically one of those two, in order to facilitate not only the safety of their system, but reduce costs and increase performance for the working set. And the replication targets can vary. So just like the HSM backing, cold storage can vary. Replication target might be another Lustre cluster, be a Lustre rsync. Looking at change logs and replicating things over the wire, it could be a completely different file system, like Azure Blob object storage. Typical on-prem usage that at least I've observed, the lifetime is generally spec'd out in years. There's a massive process of vendor selection, architecture design. Once it's actually in-house, you do a ton of testing around, is it actually achieving things we spec'd out for it to hit? Cold storage is usually selected around the same time frame to match the Lustre system and make sure that you're generally hitting the capacity targets that your users dictated. This is just generally a very long process, but it's designed for a system that's going to be around for 3, 5, sometimes more years if funding doesn't come around soon enough. There's a one-time initial stand-up cost. You're moving usually a lot of data into it at the beginning in order to allow users easier access to it, unless it's a scratch system. And associated with that is an initial Robinhood scan and DR replication, which can take days or weeks. After that, you're tracking change logs to replicate changes. So new data that's added generally is the churn. Old data tends not to change. It might be reread, but generally isn't remodified a ton of times. Robinhood and these nightly replications, as a result, are usually processing tractable amounts of churn. And finally, HSM and DR is almost never in the critical path. So users are not slowed down by these things unless they're accessing something that's just like particularly cold that they haven't touched in half a year or something. But yeah, archive and release of cold files may even be shunted to non-peak hours to avoid it getting in the way of things. So we've seen these usage patterns change a lot in Clouddeployed Lustre and Azure. And so looking at them specifically, compared to the 3 to 5 year lifetime and design around that, Lustre clusters are generally erected on demand in the cloud for days, weeks, or months, months being like on the long end of the spectrum. Scratch cleanup, I know an earlier talk discussed how fast can you delete files, and 70,000 per second was listed as like an important target or something that was observed. This is just achieved by full cluster deletion. Once you archive that stuff back down, one becomes many. So the 1 to a very small handful of Lustre clusters you're operating in your production environment will become potentially 1 per job. This is it's trivial to deploy more Lustre file systems and clients. You can avoid overfitting that way. So instead of scoping out, okay, I need 100 GPU enabled clients and 10,000 normal CPU enabled clients and all these various things up front, you can kind of deploy these on demand as the job requests. Resiliency, FLR, things like that is achieved at the cloud component level rather than at the Lustre file system level. In the not so distant future, I really think people should imagine, in a PBS job, you specify how many cores do I need, how many nodes would I like them to be spread over, how much memory is required, properties associated with specific nodes, that like, does it have a GPU? And you might even have something like, Lustre file system with X capacity, Y IOPS, Z bandwidth, things like that, just as part of the job, not PBS specifically, but that mental model, I think, holds in terms of where Lustre in the cloud might go. And then finally, a fully amorphous cold tier with object storage being kind of an underpinning part of any cloud vendors offering HSM, this cold storage design planning process really isn't a singular sizing at the beginning to be done, but rather a recurring exercise in when is this data fail to have any value? Like, when is it worth getting rid of in order to save costs? And so some of the architectural challenges that spin out of these new use patterns when you're trying to use Lustre HSM to achieve some of these things in the cloud is, first of all, from a performance perspective, Lustre HSM really enters the critical path. When you launch a new Lustre cluster, and that's associated with a job and a subset of the massive tree that is your multi-petabyte on object store is hydrated. On job start, you really want to hydrate all that metadata prior to handing off to the consumer the job, basically the application, so that it doesn't stumble into a file it expects to exist that doesn't exist yet. Lustre HSM import works, but is performance constrained, and I'll talk about that later. Time to restore is the next step. So once the job's actually executing, if it's highly parallel, which is common and thankfully common, if it's doing a ton of rereads, then time to restore will be less of an issue, because either the parallelism will cause restores to naturally occur very quickly, and files will be, the data will be slurped in for those files from the underlying cold storage fast. But if they're serial, or components of the job are very serial, every time you access that file, it will be found to be in a release state, and there are delays accessing that as a result. And finally, time to archive. So at the end of a job, because this is like cluster per job kind of mentality, at the beginning, you want to hydrate as fast as possible to start the job. Once the job's running, you're basically just slamming the file system for the entire duration. And at the end, you want to tear down the file system as quickly as possible in order to save costs. And because since you're archiving it back to Azure Blob or some other object storage, there is, you can do all your post-processing elsewhere. And so as a result of this no idle time pathology, Robinhood and other frameworks can really struggle to keep up with the changelog, like basically rate of changelog generation from the ingestion and then job execution. Beyond performance issues, there are some architectural impedance mismatches. Not all, there are really good matches for, and one of the reasons that we've been looking at, the HSM component of Lustre as a really good fit for this in the cloud. It's great for the initial hydration of just metadata. It's great for erecting job size LustrFS on top of an otherwise massive object store that would be onerous to try and slurp in even just the metadata of. And it's a great match for just archiving the change data. The places where there is some architectural mismatch, at least in terms of these new use cases, are directories. These aren't supported at all in Lustre HSM today. Minor file modifications, at least in today's versions of the copy tools available online, are, it's doing a complete copy back of even like a terabyte size file that has a small modification against it. Unique file types are sometimes handled a little bit, but not broadly supported. Symlinks, hardlinks, sparse files. These will frequently end up, when they're archived and then restored again, you won't get the behavior you left your last Lustre file system with. Striping and extended attributes aren't restorable via the import API today, or tracked for archive. There are some attribute changes that don't trigger like a needs archive in the Lustre HSM. And finally, directory renames. This is more of an architectural mismatch in terms of just how the file system is designed, and not something that's trivially reconcilable. But if you were to do like a move of a directory with 100 million files in it on Lustre, that's not that big of a problem. In a full path indexed object file system, this can be a massive problem, because you need to effectively do renames of every single one of those files. And so, point being, at the end of archive, what I think a lot of cloud users of Lustre really want is a mirror achieved in the cold tier as efficiently and as completely as possible. So when they come back and do a restore, it is effectively the same as when they left it. So some potential areas for improvement that we've identified, and I put tractable in parentheses here because I think these are the low-hanging fruit. There are certainly other areas that I think would be awesome to dig into. However, they might require significant change to the existing HSM framework or Lustre generally to support this in the cloud. So first of all, on the metadata hydration area, if there's a batch version of the import API, such as a single syscall that would work to import all of the files within a given directory. That would really reduce overheads that I'll show later on a later slide. There's reduced overhead checking mounts and taking locks as part of that, that API that would also help. And implementing support for setting stripes or other extended attributes would really go a long ways to returning a file once brought back into Lustre to a more similar format to where our user left it. Once you get into data restoration, I mentioned super serial workloads will run into delays accessing files. If we could potentially reuse stat ahead, just call it restore ahead, a similar mentality to that, you'd have to be a little more cautious because obviously you're slurping in, gigabyte or more size files. So the heuristic, while there's parallels here, there's probably some analysis that would need to be done to figure out where that heuristic can be reused. But generally, it'd be nice to have some way to detect very serial workloads that are blocked by consistently hitting and waiting on restores to complete, or batching improvements to the copy tool API for very small files. So this is the opposite end of the spectrum, where you have millions of tiny files. If there was a way to batch up these when you send it across to the copy tool, though it can work in parallel on these files, being able to reduce RPC overhead would be really nice. And then finally, when a user goes to archive at the end of their use of the file system, the batching improvements, again, for very small file-oriented workloads would be great. And native support for directories. This is I put this in parentheses as a reach goal because it's like it toes the line with what's tractable. But having support for directories in HSM code would be awesome and would really support a trivial archive and then later restoration of them to and from cold storage when used like this in the cloud. So as a quick, we're looking at a bunch of these things in the background, and I'm sure we'll be engaging actively with upstream developers to try and figure out the best ways to get these in, because I think they'll lift all boats once improved. But one of the areas we've looked at the most so far is time to hydrate metadata, because it's right at the beginning of the process of getting a job started. So to do this, I basically just wrote a tiny benchmark program that calls into LAPI HSM import. Each thread will import 10,000 totally made up files into a directory on this node that has like 32 cores and decent networking speed. And when run, it climbs up. It starts pretty low, only like 200 to 300 imports per second. But then as you add threads, it peaks around 10 or 11 threads at around 1,700 imports per second. And this is around a quarter of the creation rate. So mentally, I was imagining that this is for a single node, that is. I was imagining that the create rate would be lower inherently because we're doing less work than a create is. This is tested with MD test with a small amount of data written as part of the create. And so imports coming in not only lower, but significantly lower was a bit of a surprise. And this was done against Lustre 2.14. I dug into this pretty superficially, I'll admit, and this is something that's ongoing. So I would love any feedback from active devs on what else I can look at, but just taking some perf data and ginning up some flame graphs, what I found was that at one thread, the on CPU time is really, really low, like 0.6% of the total CPU capacity for the node. And even at 16 threads, it only grows to just shy of 6%. The off CPU graphs demonstrate that there's a number of RPCs that the code's basically waiting on. I think it's roughly, it's definitely more than 6, but it could be up to 9 depending on my read of the off CPU graphs, and I need to do some code analysis to validate that. But most of the time is basically spent following a portal RPC set wait, and then some of the calls I even have questions about because one is set stripe, LOV set stripe, despite it not actually being supported. And so that consumes 3 RPCs to not even do anything. So I was able to improve this slightly by bumping max RPCs and peer credits. So it jumps up to like 2,400 if I crank both of those up to basically allow the client to have more things on the wire at a time. But broadly, I feel like this is a band-aid of sorts. And the import API seems to have a lot of low-hanging fruit we might be able to improve, especially if we crafted a new one that uses, supports batches of files, relaxes some of the guardrails that are in place, it checks the mount every single time you call into it. And so if we designed a few of these just slightly more purpose-built for this initial file system import, which is most common in the cloud, I think it would really increase the speed of this quite dramatically without a ton of code change. So in summary, existing HSM code lays a really excellent foundation, I think, for Lustre's transition to the cloud. I think there's a lot of applications that, of Lustre HSM in the cloud that, while achieving kind of the same thing that it achieves on-prem, it's for very different reasons, and it's stressed in very different ways. And so that first needs to be understood. Cloud vendors really need to engage with the Lustre community around this to try and see some of these things highlighted, because these are not pain points, I think, for on-prem people. I'm trying to do as much performance analysis as I can around this so that I can communicate these things. But I think the three areas that are the highlights for Lustre deployed in the cloud is hydrate, restore, and archive. And once we have really good numbers, I'm sure there'll be plenty of emails around that, and or bugs opened in Jira to kind of track these optimizations. And finally, improvements. I'm hopeful that improvements made to decrease the stress around cloud deployed Lustre will also lift all the boats of on-prem users of Lustre HSM, because certainly for their initial ingest of Lustre, or if they hit particularly busy times when there's just a ton of data churn, or you have to get an archive out because you're moving file systems for still on-prem uses. I'm hopeful that these changes will lift all boats and we all benefit from it. So at this point, I'm happy to take any questions. I am working from a single screen here, so if you can help me out, Kevin, I'd appreciate it.
Yeah, we'll do. So if you have any questions from Ellis, please post them in the chat or the Q&A. I'll start with one to kick us off. I don't think you mentioned this, but did you say which version of Lustre or you were used for your benchmarking?
Yeah, the benchmark was on 2.14.0.
Thanks.
Yep.
And in this case, this micro benchmark, you're just reading everything into this client and throwing in this benchmark client and throwing it away.
In the benchmark that I had done, it was exclusively calling import over and over again with stat data from a single file. And so it's creating 10,000 unique files, but it's using all the stat information from one file. So there's where normally you'd be importing from somewhere, you'd be statting something in cold storage and then calling import based on that. Here, I wanted to make sure that we were exclusively exercising just the import call itself. And so this stat data is just from a test file that I used to make sure that there wasn't any slowness from, I grabbed this off ext4 to make sure that following that one stat, there was no other calls to stat. Everything was waiting on Lustre at that point.
Thanks. All right, a few other questions. First from Anton. Any reason the experience would be different in a different cloud, for example, AWS?
Yeah, I have not done a ton of exercise on AWS. I actually just joined Microsoft myself last June. I was at Panasys for a decade prior to that. So I don't feel that I can comment on that. But having looked at changes upstreamed to Lustre and having tried things out on Master Next, I don't see a ton of changes that would improve it, at least right now, for the import experience, at least. So I'm inclined to believe that the experience would be identical, but I don't have any, I have no reason to comment on that outside of certainly the things that we can pull down from upstream have not changed.
Yeah, and I think the question essentially, as far as you perceive all of the performance things that you're interested are in Lustre itself, not related to any of the other elements
Right.
around it.
Yeah, all the benchmarks that I've been doing, some of that data I've not shared here, both because of time and because they weren't as fully curated as the hydration case. I'm trying as much as possible to segment both sides of the cold side. I'm exercising like Azure Blob. I'm exercising with really pointed tools. In our case, obviously it's different in Amazon or Google. And then on the Lustre side, I'm really just trying to see what the speed of light is on that side. And that's where we're running into some of these hurdles in terms of what's the speed. Getting attributes from Azure Blob, we can do very fast from a scale out perspective. And so I knew I could go at tens of thousands of blobs per second, even from a single machine. The trouble right now is really in the hydration path, at least lies with Lustre. And so that's what I've been tuning some of the parameters around how many metadata RPCs can be in flight at a given time, and got some improvements from that. But I think most of the time is spent waiting on transit time across to the MDT for what feels like too many RPCs for a single import.
Thanks. One more question.
Sure.
This is from Nathaniel R. For your benchmark, did you write your own agent?
The agent, so in this case for the hydration, there would be no agent involved. The agent is just with regard to the copy tool, at least in the parlance that I'm thinking of, agent being used as, that's on the DDM wiki. So that node would be uninvolved. For the metadata hydration, you're really, you're just calling import, whether it's your own crafted hydration tool that kind of runs through. I know within Lustre, there's the LHSM tool _ POSIX that can do some of this, and it will do both the metadata hydration portion as well as the basically queue up something for the copy tool to ingest the data. But in our case, we really would like to see just the metadata come in, because we don't know if the user has done the best job of saying, here's just the directory I'm interested in for this job. They might say, here's my entire home dir, or here's an entire project dir that can be petabytes in size. And so restoring all of it into a file system that might very well be smaller than that capacity. If it's all flash and they know their job only needs 100 terabytes or something like that, they may very well hydrate a much larger space rather than asking for it all to be restored up front. And so the agent in this example was not used at all.
Thanks. And we have one last question from James Simmons. He's asking, were you testing with the MDS RPCs and flight changes? He's specifically referencing LU 6864.
I can't open a browser to look at that. I assume that is the external coordinator changes, maybe. If it is, no, this is just 2.14.0 as it stands today. I do need to repeat a bunch of these tests with some of the changes that he has in flight. I've reviewed some of that, but not posted all of my comments on it. And thanks as always to James Simmons for awesome work. I will definitely repeat this exercise with against that bug. I'll look at the specific LU after this call and see what I can pull in to retest this.